Okay, this lesson is for Tuesday, December 13th, 2011. Today we're going to begin going over our unit on thermal energy. We're going to go through some notes, and we will have some time at the end when we finish these notes for you to go back and look at the handout that was given to you yesterday on Gardner's multiple intelligences, and you can finish that self-test on the internet. The computers will be available to you, and you can turn that in to me. The important thing also to note today, I've made the computers available to you as you go through the notes, so you can actually go to the website right now and open up the weekly agenda, and you can go ahead and click on these notes. That way, if you fall behind as this is going on, or if I haven't paused for you to clear something up, you can go back and look at something that we've covered to fill in for your notes. We are taking Cornell notes today, so it's going to be important that if you haven't picked up one of those handouts as you walked into class, that you go ahead and get one of those now so we can get started on time. Okay, so as we go through these notes, I've also included a YouTube playlist, and I'll be showing you where that is. Here to start, it'd be the first thing that we'd be doing right now, so I'll be pausing this video to show you, but I also want to show you where to get them if you're on your own. So if you go to my YouTube page right here, it would take you to the channel, and on the channel at the top you'll notice that there's this selection bar. You can click on playlists, and right here for thermal energy there's a playlist, and if you click on that playlist, it'll show you the videos that I've selected for these notes on thermal energy that we're actually going to show today. They're all really good videos that highlight some of the key principles that we're going to be discussing today. So if you want to go back and take a look at this even after class, you're welcome to do that. Okay, so we've already watched that video on Bill Nye, and you saw some pretty interesting information that's going to kind of lead us into these notes that we're going to be going over. So today's notes are on temperature, heat, and thermal energy. Today it's going to be important that when you leave, you're able to explain how temperature and thermal energy are related to each other. It's going to be important that you can identify the properties of the Celsius and Kelvin temperature scales, because we use Kelvin in this class, and so it's going to be important you understand why we use the Kelvin as opposed to Celsius. We're also going to describe how thermal energy is transferred. We're going to identify conditions for thermal equilibrium, which is where temperatures can balance each other out. And then we're going to explain how a calorimeter works. We might not get to this last one in these notes, but we are going to cover it when we come back from our Christmas break. Okay. The main idea here is that heat is a transfer of thermal energy, and we're really going to focus on what that thermal energy, what makes that thermal energy, and talk about how it can affect temperature. So let's go ahead and start by talking about the fact that thermal energy is really just related to the kinetic energy of the particles. So this part right here is very important. The kinetic energy of its particles basically tells you the temperature of the object. Okay, and if we were to look at a balloon in sunlight, the energy that's absorbed from the sunlight makes the helium atoms in that balloon move faster in random directions, obviously, and they bounce off the rubber walls of the balloon more often, and the balloon will expand and get bigger. You've probably seen this with, if you had a basketball and you left it outside and it was really hot outside, the basketball will tend to seem like it's more inflated than it was before. Likewise, if you read the second example, it says if you refrigerate a balloon, you'll find that it shrinks. It does this because the particles are moving slowly. Consequently, they don't hit the outer edges of the balloon as often, and so the balloon will actually shrink and get smaller. Same thing happens if you were to leave your basketball out on a really cold day. You would notice that the basketball would actually shrink, and that shrinking is due to the fact that the air particles inside the basketball aren't hitting the walls of the basketball as often, so it appears to get flat. Now we're going to watch a couple of YouTube videos here that demonstrate this principle. One is of a solar balloon that can be made out of trash bags, and another video is going to be of some liquid nitrogen being poured on a balloon. Okay, so you took a look at those videos, and it's important that you understand that the state of matter, either if it's a solid, liquid, or gas, also has a big impact on how the particles move back and forth. So we were talking about air, and we also saw an example for well, air is a liquid, right? And we saw an example for that liquid. And in a solid, you should know that the atoms cannot move freely around, but they do bounce back and forth still. And so the temperature is actually transferred a lot quicker in solids than gases and liquids because of the fact that the particles are so close to each other. As you increase their temperature, they're more likely to bounce off of other particles and transfer that energy. So we'll talk a little bit more about that as well. Okay, so thermal energy and temperature, how are they related? You saw in the video with Bill Nye, he explained that that huge ice sculpture actually had more thermal energy than the match. Even though the match's temperature was higher, the fact that it had fewer particles made a big difference. And that's what this first statement is saying. It says the average energy of the particles that compose a hot object is greater than the average energy of the particles that compose a cold object. And this is true unless the object has a lot more particles. I mean, if there are many more particles in a cold object than the hot object, then it actually will have more heat energy. Okay. Right here, temperature depends only on the average kinetic energy of the particles in the object. So this is important to know because what it's basically saying is that the temperature for the match is going to be higher than the ice sculpture, but its thermal energy will not be, and that's where this third statement comes in. The thermal energy of an object is proportional to its temperature and the total number of particles that make up the object. If we look at these two muffins, they may be the same temperature. They're sitting next to each other. We're going to assume they have the same temperature. But you can see here in the graph that the large muffin, because it has more volume, more particles, is going to have much higher thermal energy than the small muffin. They have the same temperature, but the bigger one, because it has more particles, will have more thermal energy. It's a real key principle that you understand the difference between thermal energy and temperature. It's not always going to be that the object with the most thermal energy will have the highest temperature as well. Okay, so equilibrium and thermometers. Let's talk about a couple of definitions here to start. The first definition here is thermal conduction, and that describes the transfer of thermal energy when particles collide. So just how the energy is being transferred from one particle to another. The thermal equilibrium is a state in which the rates of thermal energy transfer between two objects are equal and the objects are at the same temperature. So if we look here at the statement, it says every thermometer has some useful property that changes with temperature. Household thermometers often contain colored alcohol that expands when heated, while liquid crystal thermometers change color with temperature. So you can see that in both these, they have a property that changes with temperature until an equilibrium is reached. So in the case of the alcohol, that's colored red usually, we used to use mercury thermometers, but those are hazardous and dangerous, so they've switched to colored alcohol. But as if you put a thermometer out on a really hot day, the molecules of alcohol will start moving faster and faster as they collect that kinetic energy and that heat, and they'll rise in the thermometer until they reach the same temperature as their surroundings. And when they reach that same temperature, they expand till they're heated to that same temperature and reach an equilibrium. That tells you the temperature outside. Same thing here with the liquid crystal thermometer. They just change color. Usually they'll have like blue as a cold color and red for the hotter colors. And they'll have like a little scale that shows you the temperature on it. So we need to go ahead and talk a little bit about temperature scales because that's also important in understanding some of the stuff we're going to do in this class regarding thermal energy and heat transfer. Okay, so temperature scales. It says here temperatures do not appear to have an upper limit, which is to say that you can get as hot as you can get with the particles moving as quickly as they can move. But it does have a lower limit of absolute zero, which is going to be negative 273.15 degrees Celsius. So that's going to be absolute zero, and that's in degrees Celsius here. The Celsius scale is something that you may be familiar with seeing in some science classes, and it's based on the properties of pure water at sea level. So the freezing point is defined to be 0 degrees Celsius, and the boiling point would be defined to be 100 degrees Celsius. The point at which you see water boiling in a pot would be 100 degrees, and the point at which you turn it into ice would be 0 degrees Celsius. But because temperature actually represents average kinetic energy of the object's particles, it makes a little more sense to use a temperature scale where zero temperature, so 0 degrees, isn't aligned to water, but let's make it aligned to absolute zero, so the very coldest that it can get. And in this case, that would be the best scale for science is actually the Kelvin scale. And the reason the Kelvin scale is the best scale for science is because the 0 degree Kelvin is equal to absolute zero. So the point at which there is zero kinetic energy in that object due to the particles moving around and that sort of thing. Okay, so let's take a look at these scales side by side. Here you have a thermometer that's reading in degrees Celsius. Here you have a thermometer that's reading in Kelvin. And then here you have a thermometer reading in Fahrenheit, which is what we use on the Weather Channel. If you see them telling you the temperature, that's what they're referring to. So if we look over here, water freezes at 0 degrees Celsius. For the weather forecasters, when you hear them say that it's going to get below 32 degrees Fahrenheit, that means that you need to bring your plants inside and that sort of thing, cover your hoses because the water is probably going to freeze for that day. For Kelvin, though, 0 degrees Celsius for water freezing is actually 273.15 degrees Kelvin. Okay, so you're going to see a lot of different temperatures, but it's just going to be important you know that the scale is pretty much the same between Celsius and Kelvin. I mean, there's 100 degrees separating water freezing and water boiling. And over here in Fahrenheit, the scale is not the same. So it's really easy to convert from Celsius to Kelvin. You just add 273.15 or subtract it if you're going from Kelvin to Celsius. But for going from either Celsius or Kelvin to Fahrenheit, there's an actual formula that I'll actually give you, and you can get some practice with it. But it's not really so important that we go over it right now. Okay, so heat and thermal energy transfer. So how is heat transferred from one object to another? And that's going to be important for us to go over. The first thing you need to know is that heat is going to be represented by a capital Q in our equation. So if you see a capital Q, that's going to be referring to heat. We don't use a capital H. So heat is the transfer of that thermal energy which occurs spontaneously from a hotter object to a cooler object, which is to say if you bring something warm in contact with something cool or bring them even close to each other, the heat is going to get transferred from that hot object into the cooler object naturally. The second statement here, thermal energy cannot be transferred from a colder object to a hotter object without work being done, is also really important because naturally the heat energy is going to want to go from the hotter to colder object. To make it go in reverse, you actually have to do some work to make that happen. It's also important that you understand that heat, our variable for heat, is going to be measured in joules, which makes sense because I just said you have to do work to move heat from cooler to hotter objects. So it makes sense that heat would be a representation of joules, energy. So if thermal energy has been absorbed by an object, Q is positive. If thermal energy is transferred from an object, it's negative. And the reason for that is because if it's absorbed by an object, that means its heat energy rose, it got higher. If the object lost heat energy, then obviously it would have a negative Q because it's lost some of its heat energy to another object. Okay, so for transferring heat from an object, then that object's heat energy will be negative, or its change in heat energy will be negative. And if we have something where heat energy is absorbed, then the object would be gaining positive heat energy here. You'll see examples of that shortly. Okay, the way that heat energy is transferred, there are 3 different ways, and you're going to have a homework assignment on this. The 3 different types of heat transfer are conduction, convection, and radiation. Examples of those: if you're to place one end of a metal rod in a flame, the hot gas conducts heat to the rod. The other end of the rod also becomes warm because the particles that make up the rod conduct that heat energy to their neighbors. So this is an example of conduction. And I know it doesn't say it, but this one right here is an example of conduction. And the reason for that is because the particles are actually touching each other, so when they bounce off of each other, it's transferred from one end of the rod to the other. A good example of this would be like if you were to if you were to grab a hot pot, obviously you try to grab it from an area, or use something to grab it that would insulate your hand from touching that pot, so you wouldn't have the heat that was transferred from the burner through the pot into your hand. So that's conduction. Convection is going to be when you have heat transferred through a fluid, either a liquid or gas. So an example of convection might be like your AC unit or your heater in your house. Whenever you heat up the air, it's flowing from through a gas form throughout your house, and it's changing the temperature. So that's going to be called convection. So heat transfers through fluids or liquids or gases. And then radiation is the last type of heat transfer, and this is through electromagnetic waves, which is basically going to be light waves. So through the sun, light bulbs, things like that. And there are many different types of heaters for your house. I mean, there's some heaters that actually work by generating a lot of heat through radiation. There's some water heaters where people supplement using a water heater by putting pipes on their roof, so that when the sunlight hits those pipes, it heats them up. So that would be a form of taking advantage of the radiation from the sun to heat their pipes. There's a lot of different types of usages for thermal energy transfer. Okay, so specific heat is going to be an important topic to talk about now that we know how thermal energy is transferred from different objects, because specific heat of a material is the amount of energy that must be added to its unit of mass to raise its temperature, which means that for different materials, they have different specific heats. Water has a very high specific heat compared to different types of metals. Metals have a very low specific heat because they tend to transfer heat energy very easily. It's going to be important that you know that the SI units for specific heat are joules over kilograms times Kelvin. Okay. So let's go ahead and take a look at some of these examples of specific heat, because I want you to see just how that might make a difference in how objects react with things around them and how they absorb heat energy from other objects. Okay, so some specific heat of common substances. So metals have low specific heats. They're good thermal conductors, which means that if you place them in an environment where they can absorb heat energy, they do it readily and quickly. Materials with high specific heats are poor thermal conductors, and examples of these poor thermal conductors are going to be usually, like if we look at this scale here, water vapor, water have very high specific heats, methanol has a high specific heat, ice has a high specific heat. So these are objects that would be poor thermal conductors. So if we were to place them in an environment where they could absorb heat energy, they wouldn't do it very quickly, which is actually a really important property of water. We use that property in water to help cool engines in our vehicles and other things like that. And you'll see that here. It says liquid water has a high specific heat compared to other substances, a property that has great effects on our climate and our bodies. Our bodies are mainly composed of water, so that gives our bodies the ability to really retain our heat energy and not lose it so quickly. Okay, so the last thing we need to go look at before we take a crack at one of these problems with heat transfer is going to be right here. It says when heat energy is absorbed or lost by an object, the object's temperature changes, which kind of makes sense. If you take away heat energy from an object, thermal energy from an object, then you're going to be making it colder. If you add heat energy, you'll be making it warmer. The formula that we're going to use is right here. So I want you to go ahead and write this down. Q is the heat energy we talked about, and it's measured in joules. M is the mass of the object. C is the specific heat of the material. So C is actually going to be dependent on what type of material we have. We would probably refer to the chart that I just showed you to find the specific heat of the material that we're talking about. The delta T here, remember delta stands for change. This would be the change in temperature. And you can see here that this formula has been rewritten. So it's the same thing, mass times specific heat times change in temperature, but they've actually shown you here final temperature minus the initial temperature. And we'll talk about how we'll set up our problems for that here in a minute. So heat transfer is equal to the mass of an object times the specific heat times the difference between the final and initial temperatures. So let's take a look at a problem. It says a 5.10 kilogram cast iron skillet. So it's an iron skillet, which is going to be important for us because we're going to have to go back and find its specific heat. It's heated on a stove from 295 Kelvin to 373 Kelvin. How much heat had to be transferred to the iron? Now if we take a look here, they've given you a nice little picture where they've identified the TF and the TI, so the final temperature and the initial temperature. Down here they've only shown the initial temperature, so you'd probably want to write in the final temperature as well. But an important place to start here is going to be to find the specific heat of the iron skillet. So let's go ahead and do that. If we go back to our chart and we look here, iron has a specific heat of 450. Notice that this specific heat of 450 is showing kilograms times K for Kelvin. If they had given you the temperature in degrees Celsius, you would not be able to use this specific heat. You'd have to find the specific heat that was using degrees Celsius. So just pay attention to that so that in the problems you do not mess it up. So let's go ahead and take that 450 and write it in. So our specific heat is also a known value for iron. It's 450 joules over kilograms times Kelvin. And we also know the final temperature, so TF is equal to the 373 Kelvin. We've actually made a mistake here. So the 373 Kelvin, they've shown, they must have mixed up 450 from the iron thing. So I'm sorry for that mess up in the example. So this should be 373 Kelvin. And again, the specific heat is equal to 450 joules per kilogram times Kelvin. All right, so we can actually plug all this information into our equation. So we've got the given and the unknown here. The equation here for heat energy is Q equals mc times the final temperature minus the initial temperature. So we'll substitute our numbers in, and we'll get 5.10 kg times 450, running out of room, so I'm not going to show this, times the final temperature, 373, minus the initial temperature of 295. So we take that 373 minus the 295, it's in parentheses, so we'll do it first, and you get 78. Multiply that times the 450, and we'll multiply that times the 5.10 when you bring it down. And that'll give us our solution for heat energy, which is going to be 179, sorry, 1,010 joules. Let's go ahead and rewrite that. Alright, so 179,010 joules is how much heat energy was transferred from the burner into the skillet to cause this heat change. Okay, so these problems are pretty simple. You're just multiplying through. There are some where they'll ask you to, where they'll give you the amount of heat energy that was either added or subtracted, and you'll have to calculate what the temperature change was, or you'll have to calculate what the specific heat of the object was. And we'll see some examples of that tomorrow, or the day after. Okay, so this last question is what I'm going to leave you with, and I want you to put this in your notes, and we'll discuss it here in class. As water heats in a pot on a stove, it might produce some mist above its surface right before the water begins to roll. What is happening? Where is the coolest part of the water in the pot? So we're going to go ahead and finish our notes here. I want you to go ahead and write down what you think the answer is to what's going on here with the mist and where the coolest part of the water is in the pot. Again, I encourage you to make sure you're taking advantage of the fact that these are on YouTube, these lessons are on YouTube, and also that you can download any handouts from the class weekly agenda.